Hi, my name is Jalen, and today I'll be presenting joint work with my collaborators at Microsoft Research and MIT. So I'll start by dissecting the title of our paper. Our work deals with cloud analytics workloads, meaning OLAP-style workloads that you might run on cloud analytics services like Amazon Redshift, Google BigQuery, Azure Synapse, or Snowflake. But even though our paper focuses on cloud services, the techniques we describe are also useful for data analytics systems more broadly. So for example, you can also apply our techniques to big data tools like Spark and on-premise data warehouses like Vertica. Now, to explain what I mean by data layouts, I'll use a running example. So let's say we're using Azure Synapse, and we load this table, where the three columns are date, price, and quantity, and each row represents some order made by a customer. So to physically store this table, Synapse will horizontally partition the table into large blocks, each of which typically contains hundreds of thousands or millions of rows. Then each of these blocks will be persisted in a compressed columnar format on cloud storage. So now let's say the user wants to run a query like shown here. Select the average price from this table, overall rows where the date is between January 10th and 20th, 2020. So this query will be sent to a compute node, which will process the query by reading each of the data blocks from remote cloud storage. So reading a block is actually quite expensive due to both I/O costs and computational costs. So we would like to avoid reading blocks that are not relevant to the user's query. And one very common technique that cloud analytics services use to skip irrelevant blocks is to maintain zone maps for each block. So zone maps are these compact pieces of metadata that store the minimum and maximum value for each column over all rows in a particular block. So for example, this very first zone map that I'm showing here at the top indicates that rows in block 1 have a minimum date of January 1st and a maximum date of February 29th, 2020. So now using these zone maps, the compute node processes the user's query by only reading block 1. And that's because the zone maps indicate that blocks 2 and 3 only contain rows after March. So data in those blocks are not relevant to the user's query. Now, on the other hand, if the user runs a second query with a filter over the price column, as I've shown here in orange, the zone maps are actually unable to help us skip any blocks because all 3 blocks contain data that's relevant to the query. So the key insight from this example is that the effectiveness of the zone maps and the degree to which we can skip blocks really depends on how we cluster rows into blocks. So in other words, query performance really depends on the data layout. So the key challenge here is how do we create data layouts that minimize the number of blocks that we need to read during query execution? So there are a variety of existing techniques for defining a data layout. So probably the most common technique is to simply sort the data by a particular column, such as the date column. But as we just saw in the previous example, this technique might not be effective if queries filter over multiple different columns at the same time. So as a result, many systems also support multi-column sort orders, for example, based on compound or composite sort keys. And some systems have also begun to support interleaved sort keys based on the multidimensional Z order. And even more recently, there's been a lot of research on what I'll call instance-optimized data layouts, where the key idea behind this line of research is to automatically optimize the data layout, often using machine learning, to achieve high performance for a particular data set and workload. Now, unfortunately, one significant limitation of all of these techniques is that they only define the layout for a single table at a time, even though real-world analytics often happens over data sets with many different tables. So in our paper, we try to address this single table limitation by introducing MTO, which is our multi-table layout optimizer. So MTO is built for multi-table datasets. For example, datasets where tables are connected in a star or snowflake schema that you would typically find in a data warehouse. And MTO targets workloads that include join queries over multiple tables, like in the example that I'm showing here in the bottom right. Now, unlike existing techniques that optimize each table's layout independently, MTO is able to jointly optimize the data layout for all tables simultaneously. And this leads to potentially significant reductions in both block accesses and overall query time. And the key idea behind MTO is to take advantage of what I'll call sideways information passing during optimization. And we do this using a construct called join-induced predicates. So if you're interested in learning more, please check out our longer talk. Thanks.